Okay, so in this particular problem, we're going to look at how we use what's called the rate law. Specifically, it's called the differential rate law. And so I'll run you through this example. Let's read through it first. We're trying to predict changes in the initial rate, how fast the reaction goes. A certain reaction is second order in nitrogen and first order in hydrogen. Use this information to complete the table below. Round each of your answers to 3 significant digits. So there are two reactants shown, nitrogen and hydrogen, N2 and H2, as well as the initial rate for 3 different experiments. So imagine it this way. You put in a certain amount of nitrogen, a certain amount of hydrogen, and then you measure how fast the reaction goes. We're not going to talk about how you measure that right now. We're not going to talk about how you get those initial concentrations, but imagine a container that has these two reactants mixed together and they're reacting with each other. In the first experiment, the concentration of nitrogen is 1.48 moles per liter, right? Molar. Hydrogen is even higher, 2.09 molar. Those are pretty high concentrations, and the initial rate of reaction is 0.572 molarity per second. So it's a fast reaction. Um, then in a second experiment, they give you the same concentration of nitrogen, 1.48, but they back off the concentration of H2 to about half of what it originally was. Now it's 0.992. And then they ask you to find the initial rate of reaction. And then they do a similar thing for the third experiment. In that case, hydrogen's a very high concentration, 5.84, and nitrogen's very low at 0.52 or much lower at 0.529. So here's what we'll do. All right. So what we're going to do is we're going to use the general form for rate. So the general form is rate, we'll use the symbol R for rate, is equal to K, lowercase k, rate constant, that's called, times nitrogen concentration squared. Now, the reason we're making it squared is because it said that it was second order. What that means is second order means it's squared. And then times the concentration of H2 to the first order. So we won't even put an exponent up there, okay? What this tells us is that the rate of the reaction, using some experiment that we don't know how, it depends on how big the rate constant is, K, and that's what we're going to find in the first step. It also depends on the nitrogen concentration squared, and it also depends on the hydrogen concentration to the first power. Okay? So it's highly dependent on concentration, and that's the main point of this section, is that the higher the concentration of reactants are, the faster the reaction is going to go. The higher the concentration, the closer the molecules are to each other on average. And if they're closer to each other, they're going to collide with each other more rapidly than they would if they were further apart. So higher concentration means they're closer. The reaction will be faster. That shows up in this rate law. Okay. Now, in step one, we're going to find the rate constant. We're given all the information to find the rate constant, K for rate constant. All right. And here's how we know that. We're given the initial concentration of both reactants and we're given the initial rate. So what I'm going to do is I'm going to rearrange this equation to find K. If you take the rate and you divide it by N2 squared and you divide it by H2, that would just leave K on the right side. So you'd have K times concentration of N. Oops, sorry, my mistake. Let me erase this. There we go. So K is equal to rate divided by N2 squared divided by H2. Okay? So we divided both sides by N2 squared and we divided both sides by H2. So that leaves K on the right side and then that would be R divided by those concentrations. Now we can just put in the numbers that are given. The initial rate for the first row was 0.572, and the units were molarity per second. So I'll write it like this, molarity per second. The concentration of N2 was 1.48 molar, and the concentration of N2 was 2.09 molar, but remember, it's squared for the N2. So make sure you square that N2 concentration, okay? And then I'm just going to go ahead and calculate that value. The value ends up being 0.1249. And what about the units? Well, the units are interesting for rate constants. Rate constants do not always have the same units. It actually depends on what those exponents are. So for the reactants, so I'm going to cancel one of the molars with one of the molars there. But that leaves us with 1 over molar squared. So that's 1 over molar squared is typically written m to the minus 2. That means 1 over molar squared, 1 over m squared, times 1 over seconds, so that's written as s to the minus 1. Now that has 4 significant digits. We're not asked to actually report the value of the rate constant. That first row is all done. It's the second and third row where we're going to use this value of the rate constant. So in the second row, they give us the initial concentrations, but they want us to find the initial rate. That's where we're going to use this rate constant. So what I'll do is I'll write for row 2, the rate of reaction is K, again, times N2 squared times H2. Okay. So for these particular numbers, our rate constant, now we figured it out in the previous part, right? 0.1249, that's what we just figured it out. And now we're going to multiply that by, in row 2, the concentration is 1.48 molar for N2. And for the H2, it's 0.992. And so for row 2, if we just plug all those numbers in, you get 0.2715. And then what are the units going to be? Well, it's the rate. So it really should be molarity per second. And let's see if that checks out. M to the minus 2 times M to the plus 2 cancels. So you're left with M divided by seconds. So M times seconds to the minus 1. Now, they only asked for 3 significant digits. This last fourth digit is 5 or greater, so we're going to round this up to a 2. Oops, sorry, that's just m, not m to the minus 1. And then times s to the minus 1. Okay, so now I've rounded the answer. Okay, so what that shows us is that once you find the rate constant, the value in the units of the rate constant, if you have the concentrations of the reactants, now you can tell how fast the reaction is going to be. We've now predicted how fast this reaction will run. Okay, now that's the initial rate. It'll probably slow down as time goes on, as the concentrations get smaller and smaller, because remember, these are reactants and they're getting used up. And then for row 3, they just ask us to do the same thing. It's really the same exercise as row 2. We just want to find the rate. So K, again, is 0.1249. M to the minus 2, S to the minus 1. That little dot means times. And then I'm going to put the concentrations in. Now the concentration is smaller for the N2. Quite a bit smaller. So that's going to make it slower. The lower the concentration, the slower the reaction will be. However, they bumped up the concentration of hydrogen a lot. It went from all the way from about 1 molar in row 2, about 1, right? all the way up to almost 6. So that's going to make it go faster. So they have essentially contradictory changes in the concentrations, lowering the nitrogen to make it slower, but raising the hydrogen to make it faster. If you really want the reaction to go fast, you want high concentrations of both of them. If you want it to go slow, then you want lower concentrations of each of them. And so that is going to give us a value of 0.2041. But again, they request 3 significant digits. So this is our last digit right there, that third one. So this is less than 5, so we just truncate the 1. 0 point, it's really approximately equal to 204 molarity per second, right? Per second, meaning s to the minus 1. Okay? So again, these are initial rates. These are how fast the reactions are going to go at the beginning of the reaction. They will go slower later on. And I just want to make one final point about this question, which is I'm going to surmise that the equation for this reaction is a very famous one. It's nitrogen plus hydrogen to form ammonia. It's unlikely it's any other reaction. This is the common reaction between those two reactants. And note that the coefficients in the balanced equation do not match up with the exponents, the orders of reactants, 2 and 1, right? So notice it's 1 for nitrogen and 3 for hydrogen. Be careful when you're looking at kinetic analysis. When you're looking at a chemical reaction, the coefficients do not necessarily match up with the exponents in the rate law. Those exponents are determined experimentally, called the method of initial rates. In chapter 15, we'll look at something called the equilibrium constant, and there the coefficients are in the expression for the constant. But for kinetic analysis, a general chemical reaction, the exponents are not necessarily matched up with the coefficients in the reaction. Sometimes they are the same, often they are, but they don't necessarily match up. So we would not conclude that the orders are going to be 1 and 3 for this particular reaction. It turns out they're 2 and 1. Okay.